Hi, this is Lab Group 3A. I'm Garrett Richards, and this is the Gaussian beam imaging. So we started off the lab by aligning this laser. It's the same laser we used last week and characterized last week. And then after that was aligned with the rail, we mounted this microscope objective. It has a 9mm focal length. It is 20x with a numerical aperture of 0.4. So we aligned that, and then we aligned a spatial filter in front of it. We chose a 25 micron spatial filter for our 20x microscope, and we took the measurement and found that 98.4% of the laser power got through, so the spatial filter is a good enough size. But first of all, to get the spatial filter aligned, we started off by placing a 100 micron spatial filter in, aligning it there. We have 3 axes of control here, and then switch it down to the 50, realign the 50, and then finally put the 25 in, and that made things go much faster when you start big and then sort of gradually get your way down small. So you see we have a nice clean beam here, and it is filled pretty much entirely by this lens here, which is good because if we had a numerical aperture that was too high, or if we had a lens with a longer focal length, the focal length of this Acumet is 250 millimeters, but if it were longer, we would have to place it farther back, and at that point the beam would be too big. It would overfill the lens. So everything is fitting here. We have a beam expansion ratio of about 2 inches over 25 microns. It's about 2,000. And the magnifying power of this Keplerian telescope system is about 27.8.
Hello, I'm Jordan. This is lab number 3, and I'm going to talk to you about the shear plate. So Garrett just finished talking about how we get the collimated light out of our Keplerian here. And so once we have collimated light, we want to confirm that it actually is collimated. So for that part, we use a shear plate. And we can see the shear plate here, and we know that from this reference line right here, if our fringes are parallel to that we are in fact still collimated. And so how a shear plate works is that light comes in, reflects off one surface here. I actually made a little drawing. If you want to take a look. Light comes in, reflects off one surface, gets reflected up, passes through, and gets reflected off the second surface. So here we have a 2-inch shear plate, and we also have a 1-inch. And we are kind of trying to design or see which one was more sensitive to translations in the optical axis. And so we can see that with a thicker plate, because the light comes in, reflects off this plate, and gets projected upward 90 degrees. And so light comes in, passes through a thicker plate. If there's a thicker plate and the light isn't quite collimated, there's more room essentially for error for the light coming in to, I don't want to say this, there's more room for error for the light to diverge and converge at different angles as it's reflected off there. And we see these fringes because we have light coming in and then being reflected up. We have interfering wave patterns, and with these thinner reflecting mirror here inside the shear plate, we have less room for error. So we did a little sensitivity test, and we found that for this 2-inch shear plate, we had roughly 0.14 microns of play along the optical axis before we could see these fringes deviate from light to dark. And for the 1-inch shear plate, we had 0.56 microns of play or sensitivity when the fringes deviated from light to dark. And that is basically how a shear plate functions and how we test for collimation. Alright, just to clarify what I just said, I want to let you guys know that it is actually the bigger shear plate that is more sensitive, not the smaller one. That's it.
Hi, I'm Ryan Kreisberg, Lab Group 3B. 3 something. Anyway, for this last part of the lab, we're profiling the beam with our knife edge, just like we did in the last lab. So here's our setup. We have our beam expander, and we go through our beam is collimated right here, and we come to a focus somewhere in this area. So we have our knife edge before our focus for this measurement, and we also moved it behind the focus to take a measurement there. And we moved the knife edge across the beam and profiled it that way. Pause. So as you can see, here's our first location for our profile. We have a very nice, clean Gaussian profile here. and we saw that using the 86%, 14% rule, that our beam was about 265 microns wide. And for our second location, it was about 215 microns wide. And we can use those two measurements to find our narrowest beam width when we start doing our calculations for the post lab. Thank you.